Trigonometry, Chapter 7, Applications of Trigonometry Vectors, Section 1, Oblique Triangles and the Law of Sines, Video 2, an Oblique Triangle Problem. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we mentioned various conditions which determined a unique triangle. Side angle side. If two sides in the included angle of one triangle are congruent to two sides in the included angle of another triangle, then the two triangles are congruent. Angle side angle. If two angles in the included side of one triangle are congruent to two angles in the included side of another triangle, then the two triangles are congruent. And side side side. If the three sides of one triangle are congruent to the three sides of another triangle, then the two triangles are congruent. We also mentioned the ambiguous case of side-side angle, which here there's too many marks, so one quick pause and we'll fix that. Much better, much better. We also mentioned the ambiguous case side-side angle. In this case, there could be 0, 1, or 2 such triangles, depending on how the given information is related to each other. In other words, if we have two sides that are congruent and an angle not between them, we can't draw any conclusions yet. In this video, we will solve an oblique triangle problem and use the results to derive an important formula. For example, in triangle ABC, suppose the measure of angle A is 32 degrees, the measure of angle B is 81.8 degrees, and the length of side A is 42.9 centimeters. Let's find the length of side B. Now, we could also try to solve the entire triangle, but let's just take baby steps. We'll find side B. So how are we going to do this? Well, since this triangle has no right angles, and you should verify that for angle C by finding its value, it's not 90 degrees, we cannot directly use a right triangle trig function. So how can we fix that? Well, let's make some right triangles. To use such a trig function, we create a right angle by drawing a perpendicular line segment from point C to side AB. In other words, we're going to drop a perpendicular segment from C, and it looks like this. Notice I moved the angle measurement for angle B outside because it was kind of in the way, but that's still the measure of angle B. Let's label the segment CD, so D is a point on side AB. And notice that this forms not one, but two right triangles, ACD on the left and BCD on the right. Now, in triangle BCD, the one on the right side, we know angle B and we know side A. So we can use right triangle trigonometry to find any side or angle in this right triangle. But which would be most beneficial? Well, think about what we're looking for, side B. And since our desired side B is in triangle ACD, the green one, and we know only one angle in that triangle, angle A, we need more information in triangle ACD, the green triangle. Now, side CD is common to both right triangles. So we can use right triangle trigonometry on the yellow triangle, the one on the right, BCD, to find the length of CD, and then we can use right triangle trig on triangle ACD, the green triangle, to find side B. So that's our plan. So let's start with triangle BCD. Now, we could go through the argument of what trig function do we need, et cetera, et cetera. We have angle B. We are going to set up a trig function involving the opposite side CD. We know the hypotenuse is 42.9 degrees. Sine is opposite over hypotenuse. So sine of 81.8 degrees is CD over A, which is 42.9. So we can solve this for CD pretty easily by multiplying both sides by 42.9. And we get CD equals 42.9 times sine of 81.8 degrees. Now, what does this equal? I don't know and I don't care. This is just an intermediate value on the way to finding B. So we're going to leave it like this for now. And now that we know the value of CD, let's shift to triangle ACD, the green one. Let's set up the appropriate trig function triangle ACD to join this angle, B, which is the hypotenuse of the green triangle, and CD, which is opposite angle A. That again is going to be sine. Sine of 32.0 degrees is CD, the opposite, over B, which is the hypotenuse. Remember, we know the value of CD will bring in its value in a moment, but for now, let's solve for B and then we'll substitute the value for CD. If we multiply both sides by B, that will get the B out of the denominator and it'll show up in front of the sign. Then we can divide both sides by sine of 32.0 degrees, and that'll get us B equals CD over sine of 32.0 degrees. But remember, we knew the value of CD earlier. It was right there. So let's take the value of CD and substitute it into our expression for B. And we get B is equal to 42.9 times sine of 81.8 degrees over sine of 32.0 degrees. And with a calculator, we can get the B is approximately 80.1 centimeters. Now, there's something more important than the value of B here. It's the expression that got us that value. Notice that in this expression, all three of the given values, the two angles and side A, are still intact. The 32.0 degrees, the 81.8 degrees, and the 42.9 centimeters. That is going to be extremely useful in the next video. But for now, you try. Pause the video and try the following. Find the value of B. Notice this is structurally the exact same problem that we had over here, where we were given the two angles on the bottom and the side on the right, side A. And now I just want you to do the exact same thing with some different values. Pause the video, give it a try. If you haven't paused the video yet and tried it, here's your fair warning. Solution in 3, 2, and 1. I'll walk through the solution quickly. If we draw segment CD perpendicular to segment AB and mark the point D on the base, then in triangle BCD on the right, we set up sine of 44.5 degrees equals CD over 19.5. So we get CD equals 19.5 times sine of 44.5 degrees. And then in triangle ACD on the left, we set up sine of 76.1 degrees is CD over B. Solve to get B equals CD over sine of 76.1 degrees. Substitute the known value for CD and then use a calculator to get that B is approximately 14.1 inches. Again, notice that the three given values, 19.5, 44.5, 76.1, are completely intact in the expression used to evaluate B.